What is recursion? Recursion is a function that calls itself within itself. So in this example, we have countdown, and it's a recursive function because it calls itself in here. A really important part of recursion is making sure you have a good base case. So the anatomy of a recursive function is in the function you have a base case, which is this else in this instance, that is your non-recursive case. So something to do when you don't want to call it recursively. And then you have your recursive case, which in this case is this if n is greater than 0, that's when you call it recursively. Anything you can do with recursive or with a iteration like a for loop or something, you can do recursively and vice versa. But this way it's much nicer when maybe you don't know how many times you need to iterate into, like the deep copy, when maybe you would have an array that is nested 5 times or 2 times. You don't know. It could be nested 100 times. Recursion is a way that you could do the deep copy where the array is nested however many times and it still works. So in this case, this for loop is pretty much replacing this if else, the base case, and recursive case. And the console logs are still in there. It's just they log at different times. So what happens with this, with a recursive case, is you have, let's say, 5 in here. It logs out 5. If n is greater than 0 it calls it with 4 passed in. So then countdown with 4 starts running, and countdown with 5 pauses. It logs out 4, then it's greater than 0, so it calls it again with 3. So countdown 4 pauses, and 3 starts. It logs 3. It's greater than, I should have said an example smaller. It's greater than 0, and then it calls countdown with 2. Countdown 3 pauses, 2 starts. It does it with 2, and then 1. So now we're at n is 1. We log it. It's greater than 0. We call countdown with 0. Now, countdown 1 pauses. Countdown with 0 is called. We log out 0. Zero is not greater than 0. So it gets to this else and it console logs. So countdown 0 then ends, and countdown 1 can resume. So that one resumes, and so on and so on, until countdown 5 ends, and then that call of countdown 5 is over. With the for loop, we know it goes from 5 to 0, and it logs out 5, 4, 3, 2, 1, 0, and then it console logs done iterating. So how does recursion work? Recursion in the synchronous world will sort of pause the function it's currently in when it's called recursively and start that new call. So when we were doing countdown, and in countdown 5, countdown 4 was called, countdown 5 paused and waited until countdown 4 finished its call. So how does the compiler know when to make the parent function wait? So how does it know to make countdown 5 wait for countdown 4 to finish? The call stack. I like to think of the call stack sort of like reading, where you're at the library, you're reading book A. In book A, it references book B. You go and grab book B. You need to finish that section on book B before you can finish your book A section. But book B references book C, so you go grab book C and you open that up. You finish reading book C, you can close that, put it down, and finish book B. But you can't finish book A before you finish book B, book C, because that information for book A is reliant on the information you're going to get from book B, which is reliant on book C. So you need to finish that top layer of the call stack, and then it pops each one off once you're done with that like section that you're reading or that function call in coding case. Similar, or for me, I tell stories not very well, and I go off on tangents, and I'll be like, so I was walking down the street, and then I saw this dog. Once I had a dog. I have to finish my once I had a dog story before I can continue my I was walking down a street story. So that's like recursively telling a story with a story call stack. So each function call is added to the top of the call stack, and then when that call is done, the function has run its course, it gets removed from the top. So it's like pancakes. When you make one, you add it to the top of the pancake stack, and then when you're ready to eat, you remove it from the top. So it's add to the top, remove from the top. You're not going to remove a pancake from the bottom. I mean, you can, but like the whole tower will fall over. So in this case, this is not a recursive function call, but we have this function that logs hello. We have this function that logs waiting. When we call say how you are, wait for a response, we'll log out waiting before we log out how are you. And similar, meet me, say hello, we'll log out before how are you, which will log out waiting, which is how are you. So it's order of operations, and order matters. So in this case, meet me goes to the bottom. So we have to finish the calls within meet me before meet me finishes. So then we have to add say hello to our call stack. That finishes. So say hello exits. Then say how are you has to wait for response. Wait for response logs out waiting. So wait for response is removed from the call stack. Now we have say how are you. That logs out. That function completes. It's done with the call stack. Now meet me is done because all of its, function-y stuff has happened. So that gets removed from the call stack. Does the call stack sort of make sense? So steps to write a recursive function. Oh, yes.
Sorry, Eric, one quick question. Could you speak briefly about how this relates to hoisting? And so, in this context, all the functions basically have the same prioritization value. I think they're all accessible, like regardless of what order.
Yeah, this one, because the ones like say how are you is dependent on wait for response, because this is declared with the var variable name equals function. It's not going to be hoisted. If these were all function wait for response type function declarations, they would all be hoisted and it doesn't matter the order. In this case though, we would have to have these two on top. And then this one is dependent up here, so it needs to be below. This one's dependent on these two, so they have to be up there. Yeah, good question. So writing a recursive function. The first thing that you should do is write your base case. And the base case is the most simple input you could give your function. So if it was, you wanted to the countdown. We were looking at the countdown. The most simple input would be the number 0, because we just want to console log out 0, countdown is done, So that's the base case. And once you have the base case, you can figure out what your recursive case is. So your base case is what you want to happen when the function should end with the most simple thing put into it. The recursive case is when it calls itself. and it is defined in terms of itself. So the recursive case will be, I don't know. I like to put the recursive case in the else, honestly, but it's just me. So the base case will be like if it's 0, then just log out done, else call countdown with n minus 1. One thing you really have to make sure you do is you're modifying the recursive case every time you do it, just because it's like a while loop. If you have while n, but you're not incrementing or decrementing n, you're going to continue that loop. Same with the recursive case. If you keep putting in the same number, 5, into countdown, it's going to be just doing the same thing. You'll get the error of like stack exceeded, or call stack exceeded, because you've just like added an infinite number of calls to countdown 5. So that's why when you saw countdown n minus 1, you were calling it on 4. So you want to change the input every time you call it recursively. And then once you have your base case and your recursive case declared, normally in an if-else, very few times do you have like a base case or recursive case not in an if-else. Then once you have that working, then you can like tweak the code to make sure, you are minus 1, that kind of stuff. So we're going to do an example. We're going to make a factorial function. This is great to do recursively. Super fun. You can do it iteratively with a while loop, but today's recursion. So factorial is, n times n minus 1 times n minus 2 till it gets to like times 2 times 1. Yeah, you can also do it with a for loop, I guess. So in this case, the first step is to define the base case. The base case here would be if n is 1 or 2, because we know times 1 times 2. Or 1 returns 0, 2 returns 2. And then at that point, then we start incrementing and multiplying times 3 times 4 times 5. So if, oops, yes, I do want to fork it. If n is 1, return 0. If, let's do else if n is 2, return 2. Okay, so we have our base cases. So most simple things we can put into it is 1 and 2. We're going to assume right now it will always be a positive number. Later we can add some like if n is less than or equal to 0, return -1. But for now we're just going to keep it super, we're going to make some assumptions. And then the else will be when we call the factorial on itself. So we have, I'm going to make these a little bit bigger. We don't need them one-liners right now. So let's think this through. So the goal is to do n times n minus 1, right? And then have minus 1, minus 1, minus 1. So we could do var new nem is n times, and then let's call factorial n minus 1. So if we put in 3 here, so if n equaled 3, we want 3 times 2 times 1. Wait a second. This should not return 0. This should return 1, right? Yeah. So we want 3 times 2 times 1. So if n is 1, it returns 1. If n is 2, it returns 2. If n is 3, we want 3 times factorial of 2, which will return 2. and then we'll return new num. So if we call, oh, if 0 is put in, that's when we want 1. If n is 0, return 1. Because we don't want, this won't add anything. But if we multiply by 0, it'll just wipe it all out. Cool. So it worked. Yay. The reason why this worked is because factorial minus 1, if this was 5, then n would equal 5, and then we would call factorial of 4. Then n would be 4. It would go through to this else. We would multiply 4 times factorial 3. So n would be 3. Then we would get to this else. We would multiply 3 times factorial of 2. We get here, and it's 2. So then it's 2, returns 2. So then we get back to the call stack of n was equal to 3. And now instead of factorial n minus 1, when we passed in 2, now it's just the number 2, because we returned 2. So then it's 3 times 2. So that gets returned to the call when n equaled 4. So then this is now, 2 times 3 is 6. So then 6 times 4. And that gets returned to when we called n is 5. So then 6 times 4 is what, 24? This is why I have computers. Times whatever that is times 5. And so that result ends up giving us 120. So does that make sense? We can, this can be just one line. And we can consolidate some of this. But these are the base cases. These are multiple base cases. We could do if n is 0 or n is 1, return 1, and then just get rid of that one. And then if n is 2, return 2. Else, this is the recursive case. So these are the base cases, and this is the recursive case. Any questions on factorial? Cool. And it's useful because then we can put 10 in there and we don't have to do a bunch of stuff. It does it for us. Sometimes it feels a little bit like a black box. When I first learned recursion, I'm not going to lie, I didn't really trust it. I was like, but how does it know? But just practice it, get used to it. Figuring out the base cases and the recursive case is the most important. And then figuring out sort of the call stack and what's going on under the hood will come with time. So this is a much smaller one, which makes sense. So this would also work. This is like a 3-liner. So the call stack with this is factorial 5 gets called. And so that was equal to 5 times factorial 4. So factorial 4 gets put on the call stack. And that equals 4 times factorial 3. Factorial 3 gets put on the call stack, which equals 3 times factorial 2. 2 is on the call stack, which equals 2 times factorial 1. 1 is on the call stack, 1 times factorial 0. 0 is on the call stack, which equals 1. So then, so because factorial 0 now equals 1, that return value gets replaced here. So it's 1 times 1. So that gets removed from the call stack because it returns. And so now we know factorial 1 equals 1 times 1. So that returns, it gets removed from the call stack. Now factorial 1 we know is 1. So 2 times 1 equals 2. it returns, so it gets removed from the call stack. Factorial 3 is 2 times 3. It returns 6, so it gets removed from the call stack. So now we know factorial 3 is 6. So that gets multiplied 24, gets removed from the call stack. Now this replaces factorial 4. We know it equals 120, so it gets removed from the call stack. Yes?
Quick question, not, I guess about recursion, but I noticed here that there's no else, it just has the return.
Yes.
Is there like any functional difference in writing else versus not?
No, I think it's a little bit more implicit or explicit if you put the else, especially when you're first starting out. But if you realize that you're doing like else return this, and it's the last line of code, most likely because you're returning in an else, you can just put return n times factorial minus 1, because if this doesn't return, then this will return. So it's sort of like it's a common pattern, definitely. Cool. Other tips for recursion, definitely start with like smaller inputs. Like I didn't put in factorial of like even 10 or factorial of 100 to see if it was working, because that's just going to be too big of a thing to sort of step through the call stack. You want sort of the most basic things put into it, like factorial 3. So you can really, one step up from your base case is sort of what you want to work through when you're writing your recursive function. And then you can test it out with bigger inputs, but starting with that one step above the base case will give you the most to work with, where you're not having to hold a lot of things in your head. A lot of times, if you're stuck, I find it helpful to write it iteratively, because a lot of these you're like, I know how to do this iteratively, but like, how do you do it recursively? Write it iteratively and then see the pattern of the function and implement that in your recursive function.
So is a lot of the examples and workshops that we were doing that we had to use the for loop, we can go back and then do recursive in those?
Yeah, definitely. Yeah, and that's a great way. Like the deep copy one would be a great one to go back to and do recursively.
Okay.
Sometimes writing out on pen and paper, or grab a whiteboard marker and write it on the wall of sort of the call stack that you want. That helps sort of do the steps of like this and then this and then this call to see where to put your recursive call. And it feels uncomfortable when you're first writing recursion. It's like, sort of like, it's not as concrete as a for loop where you can see the I. But with practice, you'll be able to sort of guess what's going to happen when you're writing them out.
So like when we're writing our for loop and we console log the index, we console log I to see if it's running through our array. Like where's the best place to do that in our recursion?
Great question. I would do that first step. So in this one, you could do this iteratively, and in the for loop, you would console log like I. Here, I would do first step before the if, I would console log n.
See, okay.
Because that would be a good spot to see, like, is n what I think it is, and is it console logging n in the order I expect it to?
Okay.
And that'll help you visualize the call stack. Great question. Any other questions about recursion? We have another lecture later today on it, but general. Okay, cool.